And we're back. So this is the continuation of Chapter 12. This is Part 2 on soils. We are still using McKnight's Physical Geography, a Landscape Appreciation, 12th edition, published by Pearson. All right, so we are just going to continue on. Soil development is expressed in two dimensions, time and depth. The longer it has time to build up, the more subsoils you get, and the deeper it becomes. There are four processes that deepen the age of the soil: addition, loss, translocation, transformation. We will get into those on the next slide. They're actually pretty easy to understand. 6 primary horizons, and we're going to look at this figure over here to the right. And the 6 primary horizons are the O horizon for organic. It's the one that's got your grass, your leaves, your trees, and all that good stuff. Okay, not just organics. The A has some too, but the O is usually a really thin layer right on top. It is literally the living type stuff and the decaying animal stuff that goes into it. Okay, so it's the O horizon for organic. The A horizon, mineral matter mixed with some humus. Okay, this is where your roots and stuff are. Okay, this is the dark stuff that's got a lot of decay and what have you right at the top. Again, usually not too thick of a horizon. It's usually rather thin, not always, but usually, especially Oklahoma, where you're talking out in western Oklahoma with grasslands. Grass don't have those larger roots for the most part, so they don't go that deep. So anyway, your A horizon. Now, because we are an agricultural society, the majority of our A horizons are actually what we call AP. And the reason we have the P is for plowed, because we've plowed them over and over and over again. The E horizon is the next one. Now, we don't really have any E horizons here in Oklahoma that I know of. All right, E horizons are for those wet areas, all right, rainforests, swamps, and the upper latitudes where you got the bogs and everything in the Arctic, okay? E is for leaching. That's that eluviation layer. We'll get into that again here in a little bit. The B horizon, accumulation of clay, iron, aluminum from above, a zone of eluviation. So this is the I zone. So everything gets eluviated down. Okay, now the B horizons, we always have B horizons, okay? We have B horizons, and sometimes we got more than one, and I'll explain that here in a minute. C horizon, this is your parent altered parent material, okay? This is your sand, silt, and your clay, all right? It's broken down, and it's usually in the form of sediment. And then we have our R horizon, which is our unweathered parent material. It's bedrock, period. It's mountains, it's rock, okay? So anyway, your bedrock usually extends up partially into the C horizon, and that's only because the C horizon may have some boulders and stuff in it. Big rocks that aren't going anywhere, they're not moving. So that can be considered a little bit of the bedrock because you're not moving it. But after that, it all becomes regolith all the way to the top, and then your soils are your B horizons and above. All right, now, is this how it actually works? No. All right, so here we go. This is how it works. So I've got my R horizon below here. I've got a C horizon in between. I've got a B horizon. I've got an A horizon. And then along comes a slight little flood type event or something, washes a bunch of sediment in and stuff, and it gets incorporated into the A horizon. So maybe I get another A horizon on top. And then I get a big flood. It just strips everything. It takes everything from this B horizon all the way back down to the R horizon, okay? Whoops, went with one too many there, put my R horizon back, okay? But then I have a stable period for a long time. And so I get a B horizon, or C horizon, I get my B horizon, I get my A horizon, and then it keeps building up. And another A, but then this here is still setting, so it becomes a B after a while. It's been setting there, it's been developing, getting harder, so it becomes a B. And then the A keeps building up, and this here will turn into a B. And then all of a sudden I get a little bit of flooding or something that comes along, and it lays down another A. And what I mean by it lays down another A, it lays down the sediment so fast that it protects and preserves the A boundary underneath. Okay, it may rot, but you can still see this dark zone under there where it was preserved. It got covered up really quick and preserved. Didn't burn off anything like that. So I get another A. So I've got A, B, 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 C, R. Okay, and then along comes a flood. And guess what? We take off the first A, we take off the second A, and we take off a B. And then we start over again. Here's my A, whoops, another little A, and these are becoming B's. And then I get some sediment load. Maybe I get a C in there or whatever. So anyway, that's how soils work. So when you go out and dig, you may see an AP and a B and a B and then a C. And the C's up on the side of a hill. Well, the rivers were up that high at one time. And then you dig down and you get below it. It's a B again. And you're going, wait a minute. Well, one of the places I go and dig, Eagle City, I've got a 22,000-year-old paleosoil. And Buffalo, I think, has the same soil. I've ran into it 2 places. We know it's 22,000 years old. It's paleosoil. It's been dated. And what happened? Well, everything got stripped off at one time, and that was just there. Here's my nice little paleosoil. And then slowly over time, these sediment loads from the stream kept covering it up. So I got all these sea horizons just lining up above it. And they preserved and protected that paleosoil, which is an A. Okay, it's an A soil. Okay, so anyway, all this big A down here, this big deep paleosoil was covered up by all these C's. And then maybe some of these C's started turning into the B's. And so I dig down and I'm like, oh, wait a minute. A soils, paleosoils are usually really, really dark. They're not red, they're black. Okay, and that's how we know they're paleosoils. All right, let's keep going. Acidity and alkalinity, acid versus base, alkaline solutions. All right, so here's my addition. This is water, okay? So how does water move? First of all, you can add water. That's precipitation, condensation, and runoff. We have lost water by evapotranspiration, and again, lost through materials and solutions suspension. So we got 2 losses here. Transformation, organic material converted to humus. Decomposition, or eluviation, okay? And transformation and then translocation. Translocation, I should say, is the eluviation. Okay, E to the I, eluviation to eluviation. All right. So anyway, these are our ones. This makes for a great A, B, C, D, E. Which one's not here? So I'm just saying you might want to remember this. All right, take a good look at it. All right. So horizons are distinct layers with different characteristics. Some of them are brown, some of them are red, some of them are white. They have distinct characteristics. And when you talk characteristics, you're talking pH, you're talking salinity, you're talking iron content, not to mention texture, which is sand, silt, and clay. What's this? What's that? Okay. And so we'll get into more about naming and stuff here in a minute. Okay. A vertical profile from the earth surface to the soil layers is considered a soil profile. This is where you go out and you hopefully find a road cut where some big equipment's already done half your work for you. But if it hasn't, it's called pick and shovel time, all right? Or if you're like me, you go out and buy an auger and auger it. A solum, what is a solum? It is a true soil. It extends only through the B horizon. Otherwise, an A, an O, an A, and a B. That's a solum. Hasn't been disturbed, and therefore we can see that it basically has been stable. Some variations on the profile. Fossil horizon sounds just like what it is. Some areas, especially if you're around a spring or even one of my mammoth sites, we find little mollusk and stuff. And those are fossils, and they're incorporated into that dirt, which makes them a fossil horizon. The one I want to talk about really here is the hardpan. What is hardpan? That is dirt that has become rock. Okay? You're not going to use a pick on it. You're not going to use a shovel on it. You're not going to use a trowel on it. You're going to use a jackhammer. All right, we have it here in Oklahoma, and it's called the Ogallala Aquifer, which is calcium carbonate. And that calcium carbonate over time has gotten thicker and thicker and thicker and turned into rock. You've got to use a jackhammer. A hard pan is rock. All right, 5 major soil forming regimes. Laterization. I don't want you to take and memorize all these. Just know laterization, tropics, red brick. Okay. You don't need to know about all the other stuff, but it's lattice soils, laterization. I've got something later that I'll show you a figure that I actually do want you to study. Podsilization, gray soil, limited vegetation, mid to high latitudes. This is up in your upper latitudes. Glyization in areas that are cool and have poor drainage. Also could be in upper latitudes. Okay, cool. These are clay soils or gray soils. Okay. Now, we do find those every once in a while in Oklahoma, but they're not what you would think. No, we didn't have a Laurentide ice sheet down here or nothing. What it is animal remains that get buried and preserved rather rapidly before the internal organs can decay those internal organs, because they go through a real slow decay once they're being preserved, will turn gray. And so you start digging into a fossil bed or whatever, and you're like, oh, what's all this gray, grayish colored dirt? I didn't think we were in an ice age or anything here, and we weren't in Oklahoma. What you're doing is messing with the decomposed remains of the internals of the animals that have been basically turned into dirt, okay? Calcification, arid and semi-arid lands, semi-arid climates with little leaching, okay? We don't have a lot of leaching in Oklahoma. Like I said, our dirt's red because of the iron, but we have very little leaching, and so we get calcification. Calcium carbonate, has to do with plant roots and filaments that once they start kind of breaking down, they pull this calcium out, and it just turns into these little nodules. You find them right associated with bee horizons. I had a whole pile of them at one dig site. When I say a pile, I mean a pile. But yeah, they're just these little calcium carbon nodules, and they will coalesce over time to create a hard pan. So they start out as little like specks, and then they coalesce and coalesce just like a raindrop on a condensation nuclei. They'll coalesce and get larger and larger and larger until they become rock. And then we got salinization for salt. Again, arid lands have that some here in Oklahoma. If you've ever been out to dig for crystals in the salt plains out there, that's salinization. Poorly drained areas in arid and semi-arid lands. It gets hot, the water evaporates and leaves behind the salt. All right, here is figure 1222, and this is a figure I really wanted you to look at because this kind of explains where you find each one. So if we look with increasing annual temperature, you have salinization. As the temperature goes down, you get to glyzation, with the laterization being kind of in the middle, okay? Again, with increasing annual precipitation, the more you have, the glyzation you get, and as you go back the other way with less moisture, you get salinization. So you should know this. Make sure you look at this figure. I usually ask one or the other which one's salinization. Laterization, I may say which one's right in the middle. But anyway, they should be pretty easy. Just you got those that are associated with hot and those that are associated with cool. Here are paleogenic regimes all over the world, and we're not going to get into these too much. You find different soils, different places. We're going to get into those a little. All right, soil classification schemes, soil taxonomy. How do we name soils? It's general classification, hierarchical system, highest level is soil order, and then we got second level, third level groups down below, subgroups and great groups. An epipedon. What is an epipedon? It is the O and the A horizon. Okay, so anytime you find an O and an A, that's called an epipedon. And then we have our subsurface or our sub horizons. Okay. So how does naming them work? Again, pH, everything goes into naming these things. If you find something just a little bit different than somebody else, whether it's slope, drainage, pH, salinity, calcification, salinization, whatever, you can put your name on it, okay? It could be the Cox soil, whatever, okay? But the naming starts getting hard. Say you've got an alpha soil that's old. It could be an alpha Uta soil. It could be a Molly Uta Oxa soil, depending on its characteristics. So I'm not going to go too far, but to say the least, it is confusing. I still struggle with naming soils because everybody can name them a little bit different. Everybody has a little general different ideal of how they go together, and so it can be rather difficult. That's pretty much all I'm going to say about this soil naming. Here we go. This is the last list of soils, alpha soils, antisoils. We'll get into those here in a second. All right, I do want you to study this table. You got raw parent material, and the first thing that happens when a soil is being created is it becomes an entosoil. That is a young soil. Doesn't have a lot of, what's the word I'm looking for here? Development. Hasn't had a lot of paleogenic development yet. Again, paleogenic, remember, is the making of soils, okay, paleogenesis. So entosoils, not a lot of development, okay? So we have our entosoils, and off to the side there, wet area, wet sites, high waters table, you got histosols. But we're going to go with entosoils. Some of the ones you should know. If it's cool climates, look off to the left, they're gelisols. Grasslands, western Oklahoma, mully soils. Dry climate, arid, should be hard to remember, arid soils. clay materials, wet and dry climate, vertisoils. Deciduous vegetation, warm and humid climates, alpha soils, eastern Oklahoma. Endosoils, andesite, volcanic. And then your older soils are your utasoils and your oxysoils, okay? You should be able to look at these and memorize some of them, especially multisoils, alpha soils are associated, and even the vertisoils are associated with Oklahoma. But arid soils, real simple, arid lands, endosoils, andesite. Endosoils are young and oxysoils are old, okay? That's kind of how you look at it and remember them. So here are 12 major types. We're not going to get into this too much. Into soils, very little development. If you will look here, you will see, when I say development, you don't see, let me put my pen on here, you don't see any development, okay? Whereas with this inceptive soil, look at this, that's starting to make blocky and angular blocky things, okay? Now, this says lack of maturity, no diagnostic horizons. Diagnostic depends on the eye of the beholder. Okay, I can see a diagnostic horizon. There is my O, possibly an OA, which is above here. And then here we have a little bit. This is different, you can tell. And there's color change here, so there's difference there. Over here on this one, look at that. There is that OA right there at the top. Okay, again, usually the OA or the AP is not very deep. Okay. All right, endosoils. I love this one. This really shows them. All right, because I've got ash mix now. I've got ash mixed with dirt. So these are endosoils developed from volcanic ash, okay? Young with dark upper layers. Here we go. All right, I can tell right here, everything below here, okay, is one subsoil. Getting used to my pen here. That's a subsoil, but then you look, there's a narrow band right there, and there's a darker band right between these two lines. And then again, right here. These are all subsoils until you get all the way to the top, and there's my O, maybe an OA in here, okay? So these are all subsoils. So this is what I'm talking about. So this is an OA, maybe another A got buried here. Then I've got these B's, maybe C's, because usually ash is considered a sediment. So these are C's with maybe a B in here. Okay, so we end up with these different subsoils. So that's kind of how they build up. Okay, gellosoils. Again, not a lot of young soil, not a lot of development here. Okay, I don't see that angular blocky stuff. All right. And I think I double clicked, so let's make sure I didn't. Okay, nope, didn't let me double click. Good. Okay, histosoils, organic saturated continuously. Okay, that's that E horizon, folks. That's the one I was telling you about. White or grayish color, however you want to, however you see it. All right, this here is that eluviation. Okay, arid soils. Okay, now got to explain something about arid lands. They're kind of different. They're kind of like volcanoes. They're dormant, they're not. Okay, so every one of these little bitty lines here is a layer. Okay, every last one of them, and it's the sand. And the sand, what happens is the sand drifts up against something, and it starts becoming stable. Okay, something blocks it from blowing away, and then you get a little bit of rain, and some bird or something drops some seeds in there, and you get a little bit of something growing, and the roots and stuff start holding it all together, like right here, this grassland, right? Okay, we got grass up here. Okay, and so it becomes stable. But let's say it gets dry again, all right? Very, very dry, no moisture whatsoever. Well, if it becomes too dry, that plant life will die off, and therefore there's nothing holding that sand and dirt in place, which means it can become active and start to blow again. It can actually loosen up as the wind hits it. It knocks those little pebbles loose and becomes a sand dune. It starts moving again until it gets trapped by something else with a little moisture and a little plant life, and it starts becoming stable again. So dunes can be active and inactive. Okay, depends on where you're at, depends on how much wind and moisture and everything else. Okay. Vertisoils, all right, here we go. That's angular blocky right there. That's what we're talking about. Okay, that's what you're going to find out in western Oklahoma. All right, and then we have some multisoils. We also have some development here. Okay, those are those A, B horizons. So here's my A horizon up above here. Here's a B horizon, and there is even another, it looks like possible B horizon there. Okay. Alpha soils, here we go, same thing, subsurface clay, horizon, medium, generous supply of cations. Here we go, it gets washed out a little bit. Here we go, this is a little bit deeper of possibly AP, but then you get down here and you can see the obvious color changes, okay? Here's my unisoils, weathered and leached of nutrients. This is what we call, it doesn't look like it's developed because you can't see these nodules like you do over here. But it is. This is what we call massive. Massive is when this whole thing is basically turned to rock. That's a hard dirt right there. You're going to have a hard time digging it with a shovel. Put it that way. Okay, it's what they call massive. That's like the final tier on development. All right, spotted soils. Hey, there's that leached out area. Just like I said, alluvial is a dark layer. So eluviation, again, leached from here into here. I'm just not good with these arrows. All right, oxysoils, mostly thoroughly weathered of soils, vegetation efficient, cycling and limited nutrients. Again, pretty much massive. You see a little bit of a color change here, but not much. And here's a map of the distribution of the United States. We have like all but 2 of them. And one of them is like ice fields. Yeah, we don't have any ice fields. Okay. All right, that's the end of chapter 12. Hopefully I will have these posted rather soon and be starting to email you all once I've gotten this all figured out. We'll go on to chapter 13 next. So I will see you in a little bit. Bye.